Alright, so Big Theta is so important that we're going to do some more examples. So, and this example is going to demonstrate a really important concept in Big Theta that sometimes people overlook, even though it can be trivial. But anyway, I'll go into that. So, now, this seems like pretty much the same function as before. But now, instead of, we just have this conditional statement. So what I'm going to do now is I'm just going to look at the bindings again and see how it happens. So if my input is input is 5, I'm going to have I equals 0, right? And then my j is equal to 0. And then what's going to happen is going to check if my I is less than or equal to n. Is 0 less than or equal to 5? And that's correct. And we return. Oh, wow, we're done. So this had 2 bindings. Okay, what if my input is something like 10? Well, then I'm going to have I equals 0. Then, within I equals 0, I'm going to have j equals 0. And then, oh, look, I'm done again. 2 bindings. And so see, what you notice is that for whatever input we have, if our input is n, we're going to get 2 bindings. So what does this mean? Well, this means that no matter what our input is, no matter how big our function gets, how our n gets, the number of bindings we get is going to be a constant number. So the runtime of this function is constant. So now this is a little tricky example because it looks like in this example that we can just say it's n squared because there's 2 for loops. But one thing with Big Theta that's really important and it trips up a lot of people. Contrary to popular belief, you actually have to understand what the function does before you can figure out what Big Theta is. So make sure you actually understand what the function does because there are tricky examples like this. So this if condition is always going to be true as long as n is a positive number. And actually if n ends up being a negative number, this the range function won't even give anything to iterate through. So it'll be constant again. So just know that this is important, that you understand what the function does before you try to figure out the Big Theta notation. Alright, now let's look at this interesting function. It's called modular. Okay, and this is again a recursive function. So we're going to use the idea of the cost model with recursion. We're going to count the function calls. So our favorite input is 5, so I'm just going to put that in there. So we're going to have input of 5, and so let's see how many function calls we get. We start off with modular 5 because that's our initial function call, and then we get modular of 4, and then when are we going to stop? When we get to a number that's divisible by 7. Okay, that's 0. So this is going to go all the way up to 0. So let me do ... just so we're clear. So how many calls is this? This is 6 calls to modular. Okay, so now what if we have our input as 10? Our next test case in most of these examples. So we have modular of 10. We have modular of 9. And then we're going to go all the way up to modular of 7. And then we're done, because 7 is divisible by 7. So this ends up with 5 calls. Alright. Sorry, not 5 calls. 4 calls. Can't subtract today. Okay. So there are 4 calls. And so that's interesting. As we increase the input, we actually decrease the number of calls. Okay. Let's see if we can think of a worst case example. Well, we know that it's going to stop when it hits a number that's divisible by 7. So let's see if we can think of a number that's very far away from a divisor of 7. A number that, sorry, let me rephrase that. Blah. Okay. What we're looking for is a number that's as far away from a number that divides 7. So one number I can think of is 13. 13 is pretty far from the next divisor. So that's then we go modular 12, and then we actually have to go all the way to modular 7 before this thing actually returns. So this actually ends up in a whopping 7 calls. Oh man. So it seems that our worst case input, so worst case, we get 7 calls. And the reason this is true is because modular 7, so because we're doing modular 7, there's always going to be, if we have n restricted to being an integer, it's always going to be the case that this ends up finding a number that's divisible by 7 within at most 7 calls, because that's how modular 7 works, because every 7 numbers there's going to be a number that's divisible by 7. So this is the key idea here. So this function actually ends up being constant. So this is an example of a recursive function that's constant. So don't think, I don't want you to have any assumptions about functions before you actually understand how they work. Some people think that if you have 2 for loops, you can just multiply through and get the understanding of what the runtime is. Sometimes that works, but oftentimes in these tricky cases, then it's not going to work like that. And some people think that recursion might lead to slower functions, so they make some assumptions and they end up getting it wrong. So don't make any assumptions. You actually have to really work it out to figure out Big Theta. Big Theta is not easy. There are many tricky examples. All right, one more function we're going to look at before we look at an actually tricky example. So we're going to look at this function that's ingeniously named function. I wonder who thought of that one. But anyway, so what this function is going to do is it's going to start at 0. It's going to have a count of 0. Hold on, let me bring this down. Don't get distracted. Okay, so we're going to start at count is equal to 0. And while it's the case that the function ends up not being 0, actually, let me make this just so it's more clear. So, oops. So we're going to have the case while n is less than 1. We're going to basically rebind n to n floor div 2. Okay, so how is this going to work? Well, let's figure out a cost model. And for this cost model, I'm going to define the bindings of n. So one question you might have is, hey, how do you figure out what the cost model is? So I did mention that figuring out the right cost model can be a little tricky, and honestly the best answer I have is whenever you're iterating through something, you want to generally look at bindings of something, and then whenever you're doing recursive calls, you generally want to look at how many times the function is called. So those are some general guidelines. Now, picking correct cost models can be very tricky, as I said, and the best way to understand how to do it is to just do a lot of practice and go through some examples and see what cost models that the explanation showed they used. So anyway, at the end of the day, if you really diagram Big Theta stuff out and you look at many examples and see if you can generalize, you'll generally get these questions right. So now let's look at the runtime of this function. So in terms of bindings of n, so if we have an input of, let's say, so in this case, I know I'm dividing n by 2. So I'm just going to be a little lazy and I'm going to make n 8 because 8 is divisible by 2. Okay, so then we're going to initially have n as 4, and then we're going to get n as 2, and then we're going to get n as 1, and then once we get n as 1, well, it's going to have to go one more time and get n as 0. Okay, so this ends up being 4 calls. Sorry, not 4 calls, 4 bindings. Okay, now let's look at another input. So I want to keep with multiples of 2. So actually, notice that I'm doing powers of 2 because what I'm actually doing is I'm dividing by 2 each time. So it's really good to just keep with powers of 2 in these examples. So you can try others, but then it gets a little confusing as to how the pattern works. So if we have an input of 32, we have n is equal to 16. We have n is equal to 8. Then we have n is equal to 4. Then we have n is equal to 2. Then we have n is equal to 1. And then we have n is equal to 0. So this ends up being 6 bindings. So now let's see if we can figure out a relationship between this. So well, let's ask ourselves, what in essence is this function doing? It keeps on dividing n by 2 until we get to n is less than 1. Okay, so basically we have to ask ourselves, how many times can we divide 2 into 8 until we get to something less than 1? So this type of operation is figuring out how many times something divides something until we get to a particular base case is the definition of a logarithm. So what we notice is that in terms of n, we can find the number of calls in terms of log base 2 of n, and then we add a plus 1 because we have a case where we have to go all the way down to 0. So now this is a little hard pattern to see, but if you check this, log base 2 of 8 is 3, 3 plus 1 is 4, log base 2 of 16 is 4, 4 plus 1 is, log base 2 of 32 is 5, and 5 plus 1 is 6. Okay, my bad. But yeah, so this is a little hard pattern to see. And if you did some more examples, you might have been able to see that every time we multiply something by multiply this n by 2, we increase the number of bindings by 1. So that's a case in point for logarithms. As the input gets exponentially large, our bindings get linearly large, and that's a true tell sign of a logarithm network. So this, I mean, again, this is okay if you couldn't figure this one out, but be aware of these patterns where whenever you divide something by 2, be aware that a logarithm could potentially be involved. Not always the case, but always map it out and see if it works. So the runtime of this function is log of n. And notice that we said log of n here, we didn't specify the base. Well, it turns out in Big Theta notation we always remove the base of logarithms. And the reason why we do that is, if you remember from Algebra 2, if we do change of base formulas on logs, the base actually ends up just being a constant. And with Big Theta notation, we always eliminate constants. So that's why we eliminate the base of a logarithm, and we just call it log of n in general. Okay. Now, before I go into some more tricky examples of Big Theta, I want to make a quick note about space. Now, a function also has something called the space complexity, which is the amount of memory or space it has used in execution. And this is also an important factor in efficiency, because you don't want functions to use too much memory, or the computer can't handle that amount of the program. So if the functions that use a lot of memory actually tend to be very slow as well. So memory and time are closely tied together. But in this course, I'm really only going to focus on the time, because I really do think if you can understand how the time complexity of a function works, space complexity is pretty easy, because you can apply Big Theta notation to quantifying space complexity. And in terms of what we can think of as a unit of memory, well, what we can think of is a frame and an environment. So every time we have a frame, we have some particular unit of memory. And also another thing to think about is when we're working with data, like lists, sets, as the length of the data increases, the amount of memory we use also increases. And this is pretty intuitive, because it takes memory to store these things. So obviously a list of length 1,000 is going to take a lot more memory to hold than a list of length 10. So this is how we can think of as memory.